All right, welcome back to our last of 3 videos on the fundamental theorem of line integrals, this one on path independence. So notice that for a conservative vector field, the value of a line integral depends only on the endpoints of the path. And what we mean by that is if you have some line integral, now granted it is the line integral of a vector field, so we need to have some, some vector field F, the wind is blowing, right? And then you've got some path through that vector field F. It turns out that no matter how you choose to get there, because this is equal to f of b minus f of a, right, where f is a potential function for the vector field. So if this is a very special vector field that has a potential function, so that the vector field is the gradient of that potential function, then the amount of work the wind does on that path doesn't depend on the path. It just depends on where you start and where you stop. And that's called path independence, which is a really interesting idea. It's very simply illustrated with a very common potential field, which is gravity, right? If you have some hill and you start at the bottom and you have a ball and you start at the bottom of the hill and you carry it up the hill, now the ball's at the top of the hill, it was at the bottom of the hill. Well, all that really matters in terms of your potential energy is the amount of height you changed. If you drove around in circles for an hour and then got up to the top of the hill, you've still changed the potential energy by the same amount. And that's why we call it a potential function, because potential energy is sort of an example of a potential function for the gravitational vector field. And so that's the idea. It doesn't matter where you start, or only matters where you start and where you stop, how much that potential energy changed. It doesn't matter how you got there, right? Now, you maybe drove around a bunch, but the change in potential energy is just the change in height, in a sense. Okay, so that's called path independence. All right, and what this means is that if it's a closed curve, so if your path C starts and stops at the same point, if A is equal to B, well then that vector, this line integral, this integral of f dotted with t ds is just equal to f of b minus f of a. But if b is equal to a, then that's going to be 0, right? And so for any closed path, any closed loop, the line integral on that closed loop will be 0 if the vector field is conservative. And it turns out that's actually if and only if. If the vector field is conservative, then the line integral for a closed path is 0. It goes the other way. If you can show that the line integral for that vector field for every single possible closed path in that region is 0, then it must be a conservative vector field. We're going to tend to use it the first direction, but it is sort of an interesting little mathematical observation that it works both ways. All right. So there's actually 3 equivalent things. Path independence, if you can show that this line integral here is equal to itself for all possible paths, then it's a conservative vector field. And if you can show that every single closed loop has a 0 line integral for all possible closed loops, then it's a conservative vector field. So these things are all equivalent to each other, and what we're going to often do is check that the vector field is conservative and then use the path independence. So that's kind of how we'll often be using it. All right, and then let's just do one example here. Find the circulation of that vector field, e to the x squared, e to the y squared, counterclockwise around this ellipse. So here we go. We got a nice little ellipse. Goes kind of like that from 3 up to 4. And it says we're going, we lost our ellipse there. There we go. And it says we're going to go, counterclockwise around the ellipse 1 time. Okay, well that means we're doing, and it asks for the circulation. So circulation That's the line integral along the curve of the vector field dotted with the tangent direction, ds. But if we can use the fundamental theorem of line integrals, that will equal f of 3, 0 minus f of 3, 0, where we started, which was going to be 0, right? It should be 0 because it's a closed loop. If f is conservative. Okay, so why don't we just check to see that the vector field f is conservative. So the vector field f was e to the x squared, e to the y squared. So that's our p and that's our q. So we need to check that py is equal to qx. Well, py is equal to 0 and qx is equal to 0. I'd say it's a conservative vector field. So there we go. There's no calculus to do. It's a conservative vector field. It's a closed path. Therefore, the integral for the circulation is equal to 0. Boom, done right there. And that's pretty slick. So there's a nice, some of these problems that look really difficult can be made to be really easy when the vector field is conservative. That's the key. All right, so hopefully that idea makes sense and you can use that to solve some problems, and we'll see you in the next video.